Hey, greetings. So welcome to today's session. So let's quickly recap what we were doing in yesterday's session. Then we will continue from where we left off. So yesterday, if you recall, we were looking at this analysis of wheel lock, or trying to figure out, like when the wheels will lock. So we consider the scenario wherein we are given a vehicle with a specific brake force distribution. Then the question we have asked ourselves is whether, under what conditions, like would the front wheels and the rear wheels are locked. So yesterday's discussion, we looked at when the front wheels would lock. So today, let's continue our discussion. Okay. So the rear wheel, sorry, sorry about that. So the rear wheel would tend to lock when FBR becomes greater than mu TW, right? So essentially, when the what happens is that, like, when the braking force is expected, it becomes greater than the maximum traction force that can be supported on the tire road interface along the longitudinal direction. So consequently, in the limiting condition, once again, what happens is the following: the limiting condition, okay, FPR is equal to mu P times W. Okay, so there is a limiting case. Okay, like when the lock may tend to happen, right? So once following the same process, since FBR now is, recall that FBR will be equal to KBR times FB. Okay, and FB from the governing equation of motion is going to be W by G times A minus F R. Right? So this is something we already know, right? From the governing equation. Then we substitute for WR. So the above equation will give us KBR times W by GA minus FRW is going to be equal to mu P times WR is going to be equal to W by L times L1 minus A by GH. Okay, so this is what we are doing. All right. So because that is the expression for WR, right? So we can immediately observe that this W gets cancelled. W gets cancelled. All right. Then what happens? Once again, we have these A by G terms which are common, right? So consequently, we have KBR times L multiplied by A by G minus KBR FRL. That's equal to mu P times L1. Once I have cross multiplied capital L, so that's why L goes to capital L goes to constant. So we follow the same process, minus mu PH multiplied by ABG. Alright, so that's what we have. Okay, so this gives us KBRL plus mu PH, alright, multiplied by A by G. That's going to be equal to mu P L1 plus KBR FRL, right? So that's what we have. Okay, yeah. All right. So that is the expression we get. So if we cross multiply, what we get is A by GR. A by GR is going to be equal to mu P L1 plus KBR F for L divided by ABRL plus H. Okay, so this is the final expression. So what does this expression give us? So the reason I put a subscript R here is to indicate that this is the vehicle deceleration at which the rear wheels will lock. Okay, this is the vehicle deceleration at which the rear wheels will lock. Okay, so all right. So this is the expression for A by G subscript R. Okay, so this gives us that value. All right. So obviously, so what this is the mathematical derivation. What is the physics behind it? So ultimately, so once again, let us say, we have a case where we have done this calculation, for a particular vehicle, and what happens is that, if the value of A by GF, let us say it comes out to be, let's say, point 0.7, right? And A by GR comes to be around 0.9. So that means that the front wheels would lock up before the rear wheels, right? Is it not? Because if you look at the vehicle deceleration per se, we will only go, what to say, to 0.9 via zero point 0.7, right? So consequently, if A by GF is zero point 0.7 and A by GR is 0.9, the front wheels will lock before the rear wheels. So if the converse is true, then the rear wheels will lock before the front wheels. That is, if A by G F is zero point 0.9 and A by GR is 0.7, we can immediately infer that the rear wheels would lock before the front wheels. Okay, so that is the physical interpretation, from this discussion. So let's write it down. All right. So the front wheels would lock before the rear wheel. If A by GF is less than A by GR. Okay, so that's what happens. Okay, so if A by GF is less than A by GR, that's what will happen. Similarly, the rear wheels would lock before the front wheels. If A by GF is greater than A by GR. Okay, so in other words, if A by GR is less than A by GF. All right, so that's what will happen. All right, so this is the main takeaway, from this discussion. Okay, so we are shortly going to discuss a few problems that I'm going to provide you as homework. Where you will essentially go do these calculations and try to find out, what these what to say values are for certain operating conditions. Okay, so this also leads us to a term called braking efficiency. So what is this braking efficiency? The term braking efficiency, denoted by eta b, is the following. It is the minimum of A by GF, comma A by GR divided by mu p plus. Okay, so that's what. All right. So the braking efficiency, okay, so as far as the parameter is concerned. So what we are saying is that, like, see, typically, as we discussed, this value of FR typically is numerically much lower than mu p. Okay, so but we can include that, right? So in the denominator, so mu p plus FR by and large is indicative of the maximum vehicle deceleration that we can get during stable braking. Okay, so that is the denominator. So in the denominator, whatever has been written is the maximum possible vehicle deceleration. Okay, in a normalized sense. Okay, in terms of GU, one can get for a road surface with a peak traction coefficient of mu p. All right. What do we have in the numerator? In the numerator, what we do is that, like, we take the minimum of the two decelerations, right? Because see, if A by GF is zero point 0.7 and A by GR is zero point 0.9, right? It doesn't make any sense for us to go beyond 0.7 for the normalized deceleration, because beyond it, the front wheels will lock and we will get into an undesirable scenario, right? So consequently, that is why in the numerator, we are essentially putting the minimum, okay? So of the two quantities. So physically, this braking efficiency is, in a sense, okay, indicative of the maximum, the numerator, okay? The numerator quantity is indicative of maximum deceleration, of course, normalized by G, achievable prior to any lockup of any wheel, okay, either the front wheel or rear wheel. Obviously, what do we want? We want this to be as close as mu p plus FR is concerned, right? So obviously, we want this braking efficiency to be as close to 1 or 100%, right? So that is the ideal scenario, but that's rarely the case. All right. Okay. So okay. Any questions on this derivation? Okay. So now, with this background, I'm just going to introduce a few problems for you. Okay. So let me go to this presentation and then I will essentially give it to you. Okay. So I think this is the next homework. Do you recall the last homework that we did? Was it homework 6?
Last is homework 6.
Homework 6, right? Is it? Okay. So let's just become homework number 7. So this is the first problem in homework number 7. So what I want you to do is the following. Let me discuss and articulate what is the problem. So we have said that a passenger car weighs 20 kilonewtons. Okay, it has a wheelbase of 2.87 Newton meter and its CG is 1.27 meter behind the front axle. So 1.27 meter behind the front axle center means L1 is given as 1.27, right? So you can immediately figure out L2, right? And H is 0.508 meter. So the brake force distribution on the front and rear wheels is 60 and 40% respectively. So that means that KBF is going to be 0.6, KBR is 0.4, right? So we are given the brake force distribution. The coefficient of rolling resistance is given as 0.02. Now, what I want you to do as a first problem in this exercise, in this homework problem, is that you find out which pair of tires, that is either the front or the rear, okay, will lock first on road surfaces with coefficient of adhesion or friction equals 0.8 and 0.2. So this initially mu p is 0.2, and then like you consider mu p equals 0.8, and then you consider another surface where mu p equals 0.2. So for each surface, please find out what will be the values of A by GF and A by GR, right? So essentially, that's the first calculation. Okay, so you can comment which pair of tires will lock, right? So obviously, which will lock first? You know, like that where the A by G value is lower. Okay, so that's what you need to calculate. And then you also need to calculate the corresponding braking efficiency and you provide your observation. Now, after you do this, next problem is to calculate the ideal brake force distribution uh, for a surface with coefficient of adhesion of 0.8. That is, initially I gave you a brake force distribution of 60-40. Now, you calculate what should be the ideal values of KBF and KBR for the essentially surface with mu p equals 0.8. Once you figure that one out, so you will get a new set of values of KBF and KBR, right? You will get KBF and KBR to be something else. Now repeat the same thing, okay? What do I mean by repeating the same thing? Like find A by GF, A by GR for mu P equals 0.8 and 0.2. And then now you state your observation, okay? So you figure out as to what changed, like how it changed, and so, right? So I think that is the problem, all right? So this is the first homework problem. Is this clear? Any questions on this? Okay. So moving on.
Sir, can you repeat that quotient of addition 0.8? Where be? How to apply? The second part of the problem.
I think your voice is breaking. Can you please repeat the question?
The quotient of addition 0.8. Is that, I mean, how to apply that?
Because mu p, coefficient of addition is mu p, right? So if you go back in the formula, right, everywhere you find mu p, right? Sorry, just mu, right? So in the slides I have called them as mu. Okay, in the notes I have replaced it by mu p. Okay, sorry about that. Okay, so this is where you need to substitute. Okay.
Okay, sir. For the mu p 0.8, we repeat AG and yeah.
Okay. Well, let me repeat the problem very carefully. There are two sub problems here. Okay. The first sub problem, I have given you a KBF and KBR of 6.6 and 0.4 respectively, right? Isn't it? Okay. So this is problem number 1. Okay. Let me call it as 1. Okay. 1, right? Roman numeral 1. Okay. So what you need to do is that you take KBF and KBR as 0.6 and 0.4 respectively, and then you calculate A by GF and A by GR for mu P equals 0.8 and mu P equals 0.2. Okay, calculate A by GF, A by GR, and eta B. Okay, the braking efficiency. Then what you do is that the second problem. So let me call this as problem number 2, right? In the same sub problem number 2 in the same. Now what you do is that forget KBF equals 0.6 and 0.4. Okay. Now you go back to this expression, this one, right? Here, substitute mu p equals 0.8 along with other data. Okay, find the new values of KBF and KBR. See, you will get two now new values of KBF and KBR. Then repeat problem 1 with the new values of KBF and KBR and state your observation. Okay, I hope that is clear. All right.
Okay, sir. Thank you.
Yeah. So any questions you can ask me in the next question. Right? So sure. Yeah. So this is problem 1. This I am going to leave you with an exercise. Okay. This is not a homework problem. Okay. So you can just do it for your learning. You don't need to submit this. Okay. So what is this problem? Let me explain to you what this problem is. Okay. So for the vehicle data provided in the previous slide, you find the ideal brake force distribution for the coefficient of friction ranging from 0.1 to 0.9. That is, you consider mu p to be the set 0.1, 0.2, and so on, right, till 0.9. Right? So then what you do is that you plot those lines on a plot where the axis are, that is the x-axis is FBF by W, and the ordinate is FBR by W. Okay. All right. So then what you do is that like you draw lines of constant vehicle deceleration ranging from 0.1 G to 0.9 G in this curve. Okay. And you draw the lines corresponding to the two brake force distributions encountered in the previous problem. You calculated two brake force distributions, right? So if you do the problem very carefully, you will see that the lines of constant deceleration will be like this. Okay, and you would have calculated two brake force distribution value. It may be somewhere here and it may be somewhere here. I don't know. Okay, you have to essentially plot this, and then like you state your observation. Okay, do each step. Okay, then the learning becomes very clear to you. As I mentioned, this is only a exercise problem for you. You don't need to submit it. Okay. On the other hand, this is your second problem. Okay, of homework number 7, which you need to submit. Okay. So what is this? So now I am giving you a four-wheel vehicle having a mass of 12,000 kilograms and a wheelbase of 4.2 meters. Okay. Then I am giving the value of L1 as 2.7 meters and height as 1 meter. The rolling resistance coefficient is given as 0.006, and let's say KBF is 0.4, KBR is 0.6. Right? So this is the first problem. So here I have given you KBF equals 0.4, KBR equals 0.6. Once again, repeat the same calculations. Find A by GF and A by GR, and figure out which set of wheels will lock first on the surface with mu p equals 0.8. Okay. Then what you do is then as a second problem, you have the same vehicle parameters. Now you calculate the new values of KBF and KBR, which will ensure that all four wheels will lock at the same time. That means that you need to find out what will be the value of KBF at which A by GF becomes equal to A by GR, right? Isn't it? Only then all four wheels will lock at the same time. I hope you agree, right? Yeah. Okay. So that is the scenario that you need to look at. Okay, in the second problem, that is, you consider which under what scenario you would have all the four wheels to lock at the same time. Okay, what value of KBF would lead to all the four wheels, both the front wheels and the rear wheels, locking at the same instant. All right, so that is the second problem of your homework. I hope this is clear, right? Yeah. Okay. Yeah. Any questions on this problem? No. Okay. So if not, we move ahead. So the next topic which I want to essentially touch upon in today's class is on stopping distance calculation. Right. So essentially, there are multiple ways to calculate the stopping distance. Okay, we will learn one way, and I will also essentially give you one exercise problem to do, so that you can figure out what to say how to calculate this important parameter. Because when we look at braking, right, ultimately the one of the important parameters, evaluation parameters that we look at is on stopping distance. Okay, so the stopping distance is the sum of this reaction distance. Okay, this is the driver reaction. Okay, so this is the driver reaction phase. Then we have the pressure build-up phase, because suppose let's say we have a braking maneuver, the driver reacts to some emergency, right? Then what the driver does, the driver presses the brake pedal, right? Isn't it? And once the driver presses the brake pedal, the pressure has to increase, right? So the distance traveled by the vehicle when the brake pressure is increasing in the brake system, okay, is what is called as the pressure build-up distance. Okay, then once the sufficient braking force is generated, what is the distance traveled by the vehicle is what is called as the braking distance. Okay, so broadly, the total stopping distance of the vehicle during braking is the sum of these three distance measures. All right. So given this, the first parameter that we need to look at is what is called as reaction distance. Reaction distance, as this formula indicates, is going to be the product of the speed at the instant of braking multiplied by the driver reaction time. So V0 times PR, right, would give us the distance traveled by the vehicle during the driver reaction. Okay, so that's what will happen. Okay, so we assume the speed to be almost constant. Then there is a pressure build-up phase. Okay, so during the pressure build-up phase, what we do is like the average deceleration. Okay, so if you plot the deceleration, this is time. What is going to happen is that like initially the deceleration will be zero, and then like it will build up, and then it will go this way, right? So during this phase, the question becomes, what is the average deceleration? So the peak deceleration will be, see, we are just using F equals ma. That's it, right? The peak deceleration will be the total braking force divided by m. Okay, we are putting an equivalent factor for rotational inertia. Okay, gamma b. But we are taking the average. So the 1 by 2 comes because we are taking the mean of the deceleration. Okay, during this pressure build-up phase. Okay, so this is the peak. So this is half of that. Okay, this is a peak. This is AP by 2, right? Isn't it? So that's what we are getting. Okay, so essentially, okay, we are denoting, sorry about this, we are denoting the average was AP, okay? So this will be 2AP, okay, the final, right? So that's why we have this 1 by 2 coming into play. And then we use simple kinematics, right? S equals ut plus half AP square, right? To calculate the distance traveled by the vehicle during this pressure buildup phase. Okay, so that is the second phase. Okay, yeah. Third phase is the braking phase. Okay, wherein this is the place where the vehicle is, what to say, is being decelerated. The brake act pressure has reached steady state value, right? It has been fully developed, and the vehicle is essentially under deceleration, right? So once again, we use simple equation from kinematics, okay, and vehicle if use F equals ma, like to essentially solve this, what to say, for the value of this braking distance, that is the distance traveled by the vehicle during this particular phase. And of course, we need to be careful when we are integrating this formula. The initial speed during the start of the braking distance phase will be this, because during the pressure build-up phase, already the speed of the vehicle would have fallen by a little bit, right? So we need to essentially incorporate that, right, before we calculate. All right. So that's how what to say, concept. So now the sum of these three, what to say, distance, right? That is the sum of this reaction phase, the pressure build-up phase, and the braking distance. Okay, will be the total stopping distance. Okay, like of the vehicle. Okay, during this. I hope that is clear, right? How we got this equation or formula, okay, for calculating the braking distance. Okay. So, as an exercise, I want you to do this problem. Once again, this one you don't need to submit as a homework. This is just for your, what to say, learning purpose. Okay. So this is left to you as an exercise. So what I am asking you to do is an alternative way wherein we are essentially going to use only kinematics to calculate the what to say, the total stopping distance. Fine. So what I have given you, it is just like I am asking you to consider a vehicle of mass 1000 kilograms and let it be traveling at an initial speed of let it be traveling at an initial speed of 100 kilometers per hour, and we have been given that the driver reaction time is 1 second. So we can see that during that phase, like the deceleration is going to be very close to zero, and the brake response time, let's say, is 0.25 seconds. Like during which also the essentially the deceleration is very close to zero. And this is another way of calculating stopping distance. Like we consider the deceleration rise time to be 0.3 seconds. So you can see that we are defining rise time as we discussed in dynamic systems, right? So the time interval that elapsed between 0 to 100%, right, or the final value, right? So that's what we are calling as rise time. So this is an ideal curve, right? So essentially, we are essentially saying, hey, look, if A bar is the final deceleration, rise time TR is the time taken for the deceleration to go from 0 meters per second square to A bar meters per second square. Okay, so that's what we have. Then the first subproblem is the following. I want you to derive an expression for the stopping distance in terms of VI and the parameters indicated in figure 1. So what do I mean? You need to, using basic kinematics, you need to derive equations, an equation for stopping distance that relates VI, A bar, TD, TB, TR, right? So these are the various parameters that are available, right? So as far as this derivation is concerned. Then what you do is then, like, you substitute the values. Okay, first derive a general expression. So I have mentioned that derive a general expression. Then what you do is that, like, you substitute the values given. Okay, and I am giving you that A bar is 6 meters per second squared. So please substitute all those values. Then you will get a value for stopping distance. Okay, then the second problem which I am asking, see, the first problem is the stopping distance. If we look at it, the total stopping distance, okay, is going to be some function, right? So if I call it as S, okay, so the total stopping distance is going to be some function of these 5 parameters, right? So that is the first problem, right? So once we do this problem, what I want you to do is the following, right? The second problem, the stopping distance is given as 75 meters. Okay. Now find A bar. Okay. Once you find A bar, calculate what should be MA bar. Right. So that is the second problem. So if you read the problem 2 statement, what I'm asking you is that, like, determine the brake force, neglecting other retarding forces that needs to be applied if the same vehicle has to be stopped within a distance of 75 meters from the same initial speed. That is, the value of VI is the same, but however, what we need to do is that now I want my stopping distance to be 75 meters. The question is, what will be A bar, okay, that we need to have, and consequently, how do we go about that, right? So how do we find A bar and then calculate the total braking force, right? So that comes out. Okay, so that is the second problem. Okay, then what I want you to do is that, like, once you derive this expression and go through this process, you would have figured out another way of deriving the expression for stopping distance and applying it, right? Would you not have? Then once you have done this, what I want you to do is that I want you to compare it with the approach that we just discussed. What was the approach that we just discussed? No, what was there in these 3 slides, right? That is the reaction time, pressure buildup, and braking, right? So you compare it with whatever we have discussed on a qualitative level, not quantitative level. So you find out what are the differences, right, and similarities in the two, what to say, two methods, right, in both the methods, and then, like, you need to comment on. Okay, so that's what you need to do. All right, as far as problem is, give a broad comparison between the two. All right. I hope this exercise is clear. Right? So, any questions on this? Okay. So once again, please note that for homework number 7, what I want you to do is submission are the problems which are listed on slides 28 and 26. Okay, the other problems are for your exercise. Okay, you don't need to submit it as homework 7, but I would advise you to do. Okay, and if you have any questions, please what to say, we'll discuss it in the upcoming classes. All right. Okay. Sure. Okay. So let's move on to the next topic that I wanted to discuss in today's session, which is on discussing the corresponding IS standard, right? So the Indian standard for braking, and one important parameter that comes out of it. Okay, so this figure I have taken it from this standard IS 11852. Okay, which essentially what is it, gives us the standard for braking of road vehicles. Okay, so if we look at this standard, without going into the details of each and every parameter or variable indicated in this plot, we can immediately observe that this is primarily a plot of v versus time and acceleration versus time and distance versus time. Okay, so that is what we have essentially can observe, right, from this particular plot, okay, taken from the standard. Now, what I want you to concentrate are these two parameters, T6 and T7. What are these T6 and T7? T6 and T7 are marked here. Sorry for the small font size, but you have to look at this plot which is marked 2. Okay, this plot 2 is for the deceleration. Okay, plot. All right, what we essentially plotted. So if I want to go back, so this point is T6, and the point where the vehicle stops is T7. Okay, so I hope it's clear from this plot what IS 11852 calls this T6 and T7. All right, yeah. So T6 and T7 indicate the instance of time at which the deceleration first reaches the stabilized value, the final steady state value, which is T6, and T7 indicates the the time instant at which the vehicle stops. Okay, so considering these two parameters, like there is another important parameter which is defined by IS 11852, okay, to characterize vehicle braking in addition to stopping distance. Okay, that is what is called as the mean fully developed deceleration, okay, or abbreviated as MFDD. So what is this MFDD? The mean fully developed deceleration indicates the mean value of the deceleration over the period of the fully developed deceleration, okay, which is T7 minus T6. Yes, in the ideal world, it should be a constant. But as you can realize, when the vehicle is being operated, it is not going to be a constant, right? There can be some variations in the deceleration, right? So once the deceleration settles down, okay, once the brake force builds up and then reaches a steady value, around about a steady value, okay, of course there are going to be some perturbations and changes in there, right? We can see that if we integrate the vehicle deceleration over this period T6 to T7 and divide by the difference of T7 and T6, okay, we are going to get this mean fully developed deceleration. All right. So this is also a very important parameter because the standards will also specify what will be the expected mean fully developed deceleration, okay, that a brake system can achieve, okay, when we are essentially driving the vehicle. Okay, so I think that is one more important parameter, okay, in addition to stopping. Okay, of course, the standard IS 11852 discusses more details on braking system performance and even IS 11852 has 9 parts. part 1 to part 9. Okay, each part deals with various aspects of the braking system performance. Okay, yeah. So that's the next concept which I wanted to share in today's session. Fine. Any questions on the material that we have discussed? Okay. So,
yes, sir, actually, we'll do this. I think we'll have to do this right before we come across any question. If there is any, we'll ask you in the next.
Sure, absolutely.
Class.
Absolutely, yeah. Absolutely, right? So because these things, the reason is that like I want you to try out first, right?
Yeah.
And then you come back to me with questions, right? So rather than what to say, I deriving all the equations, right? So it will be good if you do this problem and the previous problem as exercises, so that you will get a feel, right, as to what is happening, right? So absolutely. Please do it.
Yes.
And do share any questions, okay, that comes up. All right. But that is why I have given only 2 problems as homework 7 for submission. The others are all like exercise problems, but I would strongly encourage you to do that. All right. Fine.
Sure, sir. Actually, this weekend we have I see engine midterm exam also. So we'll do this on Sunday. We'll try to complete maximum possible.
Yeah.
And
yeah, I will give you 10 days to do it. Okay. Like, so the deadline for homework 7 will not be this Sunday. Okay. I will give you, what to say, next Sunday to do it. Okay. I will post it in the classroom. Okay.
Okay, sir. Thank you. That will be good.
Yeah, sure.
So before we do that, one question on this MFDD. So from this figure, it shows like at T6 or T7. So does it mean like it is having different acceleration, or it will be the same acceleration?
Yeah. So ideally, if you look at the ideal figure, it looks like the same, right? But in reality, it won't be, right? So that's the point, right? So see, once you sort of like reach a steady state, okay, when you do experiments and so on, right? You sort of like figure out, when you are within a certain band around the steady state, right? But the deceleration value is going to vary, right? So you figure out T6 to T7 and then like calculate this mean fully developed deceleration. That's the idea, right?
Okay.
Okay. So yeah, if you look at the ideal figure, it looks like constant, right? So then the mean fully developed deceleration should be this A bar, right? Isn't it? Right? Yeah. But this is an idealized curve, right? So isn't it? Right? So in reality, it won't be like this, right?
Okay, so maybe once we do this, then we understand that clearly.
Yeah. Please do that, right? So, all right. Any other questions? Okay. So if there are no other questions, what I will do is like I will stop our discussion for today's session here. Thank you.